So welcome. We're continuing with this this particular chapter, and we've just finished talking about what happens when you add heat to a solid, and it warms to its melting temperature. Then it melts, and then the liquid warms to its boiling temperature. Then it boils, and then the vapor warms. We can play various games with that, but there's other physical things happen when we add heat to something, and one of them, for example, is things expand. So, and I'm trying to show you in the diagram some things to do with that. So, for example, and this is, I believe me, this happens, and that is you have a filling in a tooth, and they use a mercury amalgam. It's safe. But it's a different material to your tooth. And what happens is, first of all, if they used any old thing, it would be a real problem because your tooth expands and contracts with temperature, and that filling will expand and contract with temperature. And if they don't expand and contract to the same extent, and the tooth expands more, then your filling will drop out when your teeth get warm, or the filling expands less than the filling expands more, then the filling will crack your tooth as your mouth gets warm. I got to tell you about that is that what tends to happen is, as you get older, if you have fillings like that, they tend to fracture the tooth. I've had my fillings for probably 40 years, and about 10 years ago I started cracking teeth. One edge of them would break off. And the dentist would say, yeah, you got these fillings, they're going to do it. All of them are going to do that in the end, kind of thing. So you go to crowns, which are a lot more expensive. But even other things like, for instance, if you're making concrete, they tend to use rebar inside concrete walls to give it some structural strength. And again, if the rebar expanded at a different rate to the concrete, then it would cause fracturing in the concrete because it would stress it. So that's an issue. And then with bridges, clearly if you have a metal bridge and it gets a hot summer's day, the metal's going to expand, and over a bridge the length of, say, the Sunshine Skyway, that's going to be a big expansion. And so somehow you've got to make it so that the bridge can accommodate that. And what they do is they use these teeth at the end, where basically the two bridges, the two parts overlap, and if they expand, they push into each other, but there's space. And if they contract, they pull apart, but they never separate. So this stuff is important. If you think about it, in an automobile engine, you want some bits to be wear resistant, like your piston rings and the inside of your piston. You want other bits to be light, like you don't want a cylinder head that's really heavy. You tend to use different materials for different jobs within a single engine. And all those materials have to fit tightly together so that you get good compression at low temperature. And you can take your car to Alaska, it's going to get really cold there. Maybe you need a little heater for that. Or you can go to the desert and leave it all day in very high temperatures, and it's still got to work. And so there's an awful lot of engineering takes place making alloys that have just the physical properties that you want. And so they have what they call designer alloys, and you go and you say, I want something that's going to have this amount of expansion and this amount of thermal conductivity and this kind of density, and they'll do their best to kind of get you a material like that. If they're lucky and they can find one, it will be incredibly expensive, so you don't use it on everyday things. But even on everyday things, as something is made that's useful, then they will produce that as a commercial material. Then it's available to the designers at a much lower cost. So there's a big revolution. The reason why the automobile today is much better than the automobile, even when I started driving, is because of materials design, basically. When I started driving, you would never turn your car engine off if you were driving. You would start it and you'd say, oh, it started great. And you'd drive to work and you'd turn it off. And as you walked away, you'd say, I hope it starts when I get off work. And you'd come back. I mean, I had an oldish car, but It was all manual. Everything was done by the position of the little spark gap, and I'd say every 2 months I was under the hood fixing things because of this. And when I came to the States and saw just a newer car with vacuum hoses, I couldn't figure out why these vacuum hoses there. What's going on here? The engine was full. And it was all sensors because they were using electronics to start controlling things. And now it's all computer driven. You probably have 5 computers in your car at least. And you basically plug it in and you turn it on. And the idea of a hybrid turning off the engine when you're at a traffic light, I just find it's eerie. It's like it goes against all my training is you don't turn the engine off. But they can do it because they can make electronic devices more reliable because of developments with semiconductors. They can make materials more reliable because they develop better thermal conductivity, better thermal expansion, so on. So it's a much different instrument than it used to be. That's all material science. So this is an important thing. So what we say is that every day I do this. Every day, every class, I forget to get the pen going. So let's go back. So, okay, we have our original length, and we have our original temperature, and then we have our new length, and we have our new temperature. And basically what we say is that our new length will equal our original length plus a little bit. And this little bit is, well, the original length times this little coefficient of expansion times the temperature change. Delta means change in temperature. And that should be not a dt down here, that should be a delta t. It's the Greek letter d. So if you plot a graph over a limited range of temperatures, you have a nice linear change with temperature. Not all materials have the same value. Some expand more, some expand less. So for each material, you'll go to a handbook and you'll look up what the coefficient is, what this little alpha is. And then you can figure out what's going on. Engineers use those handbooks or they go online. There's a Merck book over here. In Britain, it was the CRC book, I guess. Not all materials expand when they get hotter. There are some weird materials that don't expand. And one of the classics, actually, is water. Here's an interesting thing. If I have a pond and I have water in it and it gets cold, if water simply got denser because it contracted, if water got denser the colder it got, then eventually you get to 0 degrees C water and that would freeze. And that would be at the bottom of the pond. And then as it got colder still, well, that water would freeze. And then, well, all the water would freeze. And any fish that were in the pond would be forced to the surface. I mean, you know, it would freeze from below them. And we could just go and pick the fish up and, you know, fishing would be easy. We'd just wait for a cold day. Actually, the first fish to ever have been produced would have died, and we'd have not have any fish, actually, when you think about it. But what happens with water is that this weird thing happens at about 4 degrees Celsius is the densest water for fresh water. 4 degrees Celsius. So that sinks. And 3 degrees is above it, and 2 degrees is above it, and 1 degree, and 0 degrees is at the top. So you freeze at the top. And ice is a really good insulator. So for the rest of the winter, this stays at, you know, 1, 2, 3, or 4 degrees. And the fish can live in this all through the winter and not be frozen out. So it's a really weird property of water that's just, water is like a really amazing thing. It has such interesting properties that are very useful to us. I mean, it's like, yeah, yes?
It's not the same thing as like you put a water bottle in a freezer, something like in 4 degrees, and then you take it out and you shake it. It's like it's frozen.
So, I don't know why that is, but I've heard about it, yes. I don't think it is because of the striations. It's called supercooled water, and it's something to do with nucleation sites. It's got to be clean water, and so when you shake it, you kind of put bubbles in it, and those bubbles act as the nucleation site, I think. So it's not quite the same as this, but it's that is a very strange behavior. It's really quite eerie what goes on with that. So some examples. Pyrex, that's a kind of glass. I lost my pen again. And then copper, and then aluminum. So this, that's joules per kilogram. That's not what I'm talking about. That's something else. Okay, that's something else. Those units are wrong. If this is right, if you think about it, this alpha, the units for alpha should be, well, it's a length over a length divided by a time. So alpha is units of 1 over degree C. It's got weird units. Okay. Let's talk about the way that things can get from the hot object to the cold object. There are 3 ways. There's conduction, convection, and radiation. Let's actually just briefly discuss them. Conduction. Conduction occurs primarily with solids. Because what happens is you have a series of atoms, and as this one vibrates more, it transfers energy to that one, which transfers energy to that one, which transfers energy to that one. And it kind of relies on the fact that they're in good contact with each other and that one vibration will affect the other one. We say that energy is transferred atom to atom, and the atoms cannot move past each other. I think of it a bit like having a series of people, and they're trying to put out a fire. So here's a fire, and here's a pond. And they've all got buckets. What they do is this person fills a bucket, and then he passes the bucket, and he passes the bucket, and he passes the bucket, and he throws it back, and then he passes the empty bucket back. So the bucket moves, not the people. That's conduction. Now, in truth, if I have a trapped volume of liquid that's small, like a little bubble of liquid, or a trapped volume of gas which is small, then I won't get much motion of the atoms past each other, and I can think about the conductive properties of the gas. So it's not that gases and liquids can't have conductive properties. It's just that you've got to be a bit specialized to find them, to get them to dominate. Whereas solids, they dominate. The alternative is convection. And convection is a series of atoms which can move past each other. So this guy gets hot and it goes high. And this guy gets hot and it goes high. And these guys are not as hot, so they go low. So everything's moving past each other. And it's a bit like having a group of people, and there's a pond, and there's a fire, and they do their own thing. Each one's got a bucket, and this guy goes along here and pours the thing out, and then it runs around, and he avoids other people, and he comes back and he goes along here, and he runs around, and he avoids people, and he comes back. So it's chaos. But it works. And that's convection. And that happens primarily in fluids and air. Have you ever been swimming in the bay or the ocean and swam into a cold patch of water. It's like it's warm, it's great, and then, whoa, it's cold, and you go back again. That's hot water rising and then cooler water sinking. It's to do with the colour of the bottom in many cases. If it's a dark colour, you'll get different temperature generation. And have you ever been in a room where somebody's dropped a bottle, say a bottle of cleaning fluid or maybe perfume or something like that, and you won't smell it, and then suddenly you'll smell it, and it's suddenly quite strong. And actually, if you're near the walls, you'll smell it before you smell it in the middle of the room, because it tends to be that you get convection near the edges rather than in the middle. So convection is very dominant in fluids if it's a big enough space to get temperature differences. You need a temperature difference to get convection. And in a little package of water or a little package of air, it's hard to get a temperature difference. So if you have a water bottle, you won't get much convection unless you're really heating it at the bottom and not heating it at the top. If you just put a bottle on a shelf, even though it can flow, it probably won't flow that much. And then the last one is, so this is energy flow, and the atoms can move past each other. And then the last one is radiation. Radiation is just photons, just like I glow. Everything above absolute zero glows. I glow, I just send out a photon. And the interesting thing is the photons are different colours. So something that's at about 5,000 degrees glows with yellow as the dominant colour. And something that's about 10,000 degrees probably glows in the infrared. In the ultraviolet. But we see the blue end in our eyes. And if something's only about 500 degrees, it might be infrared and we won't even see it. We chose, as animals, to make our eyes sensitive to the reflected photons of the sun. So we look at light in reflection. We simulate the sun with our lights. When the sun goes down and you turn the lights off, you don't see anything because there's no sunlight being reflected. Maybe you get some sunlight from the moon because it's bounced off the moon, but that helps. We're very sensitive to that. But if you're in a room and you close the blinds and you close the door, you're in darkness. But that room is full of light. It's full of infrared light. So everything from the coldest ice cube, liquid nitrogen, everything above absolute zero glows. If it's below room temperature, if it's below the temperature of a ring on your stove, it glows in the infrared. If it's above the temperature of like a propane torch or something, it glows in the ultraviolet. Now, usually not just one colour, there's a spread of colours, so you might see a little bit of red, but there's mainly ultraviolet and so on. A little bit of red, but it's mainly infrared, whatever. So we see this very narrow band of things. So when you see your stove ring glowing, it's a bit unusual. We're seeing the glow that's always there, but as the temperature changes, it's a different colour. And so we sell cameras that do that kind of thing. I was in an exhibition. I worked for a company which made electron beam instruments, and I was in an exhibition hall, and there was a company that sold infrared cameras. And the trick, the party, everybody has something to get the crowd kind of interested. And the trick that the other company did was they'd have a camera set up, and one of the sales guys would put his hand in front of the camera, and he's looking at infrared, so you can't see infrared, so they use a computer to make it look a certain colour on a screen. It looked blue. And then he lit a cigarette and inhaled a cigarette, and his hand just changed colour. That's a temperature difference on the hand because it's constricting the blood vessels. So for medical imaging, this is great. You can look and which bits are hot, which bits are cold. For following footprints on a cold night, as somebody walks down the street, you can follow their heat footprints. Thermal cameras the police uses, this is all that kind of stuff. You got a question or a comment?
So basically, the scientists apply that concepts to determine what's going on the other planets.
Yes.
The temperature and stuff, materials.
That's exactly right. What happens is that, if you think about it, all of astronomy comes from optical telescopes or radio telescopes or the like. And for the longest time, we were limited by optical telescopes on the Earth's surface. So we could see red stars, we could see blue stars, and yellow stars like our sun. And we could infer the temperature from that. And that's about all. There were some other things, but we could actually do a lot more, but that's... And then along came radio telescopes, and we could start looking at parts of the universe that were colder. And we discovered all these like cold clouds that we didn't really see before. And then more recently we put telescopes, first of all into aeroplanes, and then into satellites. And these guys can look at very high energy radiation, X-rays and gamma rays. They're very hard to make telescopes. They're very penetrating, so your telescope has to somehow stop them and measure them. But they can do it. It's hard, but they can do it. And so now we can see gamma ray sources and X-ray sources. And so our view of the universe, just in the last 40 years, has changed tremendously because of all these different things. We infer from all of this expansion of the universe, the age of the universe, the way that the stars develop and the like. All of that is from looking at light. It's the most amazing thing. Let's go a bit more detail. So this is a block of material, and we have a cold end and we have a hot end. It's got a certain length and it's got a certain area. And we'd like to know how much energy flows down this thing per second. If it's a big temperature difference, I expect a lot of energy to flow through. If there's no temperature difference, no energy is going to flow through. If it's a long rod, less energy is going to flow through because the ends are further apart. The hot and the cold are further apart. If it's a short, thin piece, the hot and cold are near each other, I expect more energy to flow through. Bigger area means there's more avenues for energy to flow. So I quantify what's going on in terms of power. And power in watts. And that equals the amount of energy, the energy per time. And sometimes I write the amount of energy per the amount of time like that. Doesn't matter, it's just nomenclature. And, well, if the area is bigger, I expect more energy per second, which is more power, so put area on top. And if the temperature difference is bigger, then I expect more power, so put the temperature difference on top. And if the length is bigger, these temperatures are further apart, so put L on bottom. This is how you make equations. You say, my parameter A. If A gets bigger, does P get bigger? Yes, it does. Put A on top. If delta T, the temperature difference, gets bigger, does P get bigger? Yes, it does. Put delta T on top. If L gets bigger, does P get bigger? No. The power decreases. Put L underneath. And sometimes, because sometimes you have lengths and lengths squared, sometimes you look at symmetries, and if it's spherically symmetrical, you put a square there. This is not spherically symmetrical, so we just leave it as L. And then the way we go from these relationships to an equal sign is we put some constant in. And we put a little k in this case. And sometimes the k turns out to be 1, so you don't bother about it. And sometimes I call the k g because I want to specify it as with a different letter. But pretty well, most equations have some constant in them somewhere to make the numbers work out right. And we just find out, we'll look that up. So we say K is the material's thermal conductivity, and then A is the area of the sample, cross-section, not the whole surface area, but that cross-section. And delta T is the temperature change between one end and the other, and L is the sample's length. And without using math, we can say, how does the power relate to the area? And you'd say, well, as the area goes up, so the power goes up, so that's a straight line. And how does power relate to the length? Well, we see that as the length goes up, the power goes down, so that's an inverse. And what about temperature difference? As the temperature difference goes up, the power goes up, that's linear. So can you see how you get those graphs from there? It's basically looking at the relationship and saying, if this changes, how does that change? These values, okay, they're manufactured. They make materials with different values of K. So you have different expansion coefficients? Yeah, I can make it for you. You want a different thermal conductivity? Yeah, I can make it for you. Or more to the point, here's a book with 1,000 materials in. Pick the one that suits your application best. My brother makes electrical motors, and he sticks parts of the motors together, and they get hot. He used to rivet them and insulate the rivets. It was really expensive. And he had this idea about sticking them together. So he didn't know what glue to use. So he phoned up 3M, and they sent him a sales guy with like a catalog full of different things. Thousands of glues, depending upon his need. And they sifted through them and found the glue that was right, because he was using, you know, this type of material, and he wanted to stick it together, and there was this temperature change, and he didn't want this expansion. It was twisting a bit, so looked up these materials with this specialized glue. It was expensive, but then he could basically squeegee the glue onto all these plates and stick them together, and he had a system that was much less difficult to make, all because of the right selection of materials. And that's what engineers do. Physicists, we don't know any of this. We just know there's glue. Engineers know there's 100 types of glue. It's like really valuable. What happens to the rate of heat flow through a wall if the area is doubled and the thickness is tripled? Okay, so what we say is power is equal to the heat flow per time. So that's what it's asking about. The rate of heat flow means my power. And that equals, well, K. It equals A. Delta T over L. Now, some people can see this and some people can't. I have a value for this P initial. Look at this equation. If the area is doubled, I'm taking that area and I'm doubling it. And the thickness is tripled, I'm taking that length and I'm tripling it. So, can you tell me, can you just try and have a go at this? Will the new rate be twice as much as the old? Will it be 6 times as much? Will it be 2/3 as much, or will it be 3/2 as much? Remembering that this is doubled and this is tripled. Okay, so can you ever go at that? Let's just see how we do. Because some people can just see this, and for other people, it's like, man, I still don't get it. And it's just the way your mind works. So what do you think? It's going to be interesting. Sometimes everybody gets it, and sometimes it's really split. Maybe one more person? There we go. Okay, let's stop it and let's have a look. Oh, so mainly people are saying 2/3, and that's what I'd say as well. So let's justify that. I'm saying, so this is how to do it. So just, let's do it a bit more formally. I can say, oh look, this is K, and this is 2A because it was doubled, and this is delta T, and this is 3L well, my K's in both, or my A's in both, or my delta T's in both. The bit that's left over is the 2 over 3. Yeah? That's a one way. You want a formal way of doing it? This is the formal way. This will always work, but it's a bit long. You say P new over P old is equal to K new, A new, change in temperature new, over L new. All divided by K old, A old, change in temperature old, over length old. And then you say, well, how has K changed? It's not. There's no information about K changing. Then what I do is I say, oh, we'll call it 1 then. It was 1 and it stayed as 1. If I don't know what it is, I'll call it 1. Then the next one, how has A changed? Oh, A has doubled. Well, I could call this 1,000 and 2,000, or 3 and 6, or 7 and 14, but why not call it 1 for the old and 2 for the new? And then my change in temperature, has not changed. So let's leave it, let's say it was 1, and now it's 1. And then my thickness is tripled. Well, it used to be 1, let's call it 3 now. All that at the bottom becomes 1, that becomes 2 over 3. So it tells me my answer. And the nice thing about this formal way is, if I told you that the answer was 7 watts originally, then you'd have written 7 watts down there. And your P new would have equaled 2 over 3 times 7 watts, which equals 14 over 3 watts. Okay? Now in Physics 1, I tend to give you that value. And it's amazing how many people will give me that as the answer. So they've done all the hard work, they've done the ratio, but they forgot to multiply by the original thing. So if you can see it, just write the answer down, you know. Right. Convection. So convection is really hard. It's chaotic, and modelling chaotic things is always incredibly difficult. So we tend not to do much about it. Physics and engineering tend to miss out the things they're not good at. So for many years, this was not really talked about. We talk about gases and fluids that flow laminarly, because we can do math on that, but not turbulent flow. But there's turbulent flow out there. The weather forecasting is all about turbulent flow. If you're making fountains, it's all about turbulent flow. You want a hydro dam, it's all about turbulent flow. So what they do is, river estuaries is all about turbulent flow. So they do models. They did an awful lot of modelling to try and figure out what was going on, but never first principles. And then back in the 80s, 70s, 80s, there was this development in chaos theory, where people started getting a mathematical handle on chaos theory. Chaos theory is the theory of systems where a very small change at the beginning makes a huge difference at the end. If you think about it, blustery wind is like that. Take 2 leaves that are next to each other, they don't stay next to each other, they go off in different directions. And yet they started next to each other. So a very small difference at the beginning makes a very big difference at the end. And in time, actually, a small time difference can make a big change. And chaos is everywhere. Hurricanes. Hurricane starts as a tiny little pressure wave off the coast of Africa. There's a story. It's kind of somewhat. It's illustrative. It's not necessarily literal. But there's a butterfly on a bush on the coast of Africa, and it's trying to decide whether to flap its wings, and it doesn't know. But if it flaps its wings now, it's going to cause a pressure wave which will grow and grow and grow and become a hurricane and hit Florida. And if it hesitates and flaps its wings now, it'll be a little pressure wave that dies out. So very little time difference makes a huge difference in the end. But there's other examples. You have a thing called fibrillation in your heart. So your heart sometimes beats arrhythmically. If that happens more than once, I think, they'll want to put a pacemaker in. And what they're saying is your heart can't be trusted, so this pacemaker is going to take over. And it takes, for the most part, a perfectly good heart, and forevermore, it makes it beat when the pacemaker says. Well, imagine that you stumbled, and the solution is we're going to have somebody who pushes you from now on, holding you, making you take steps when they say you should take steps. You just stumbled once, but from now on, you're not in charge of taking steps. It would drive you crazy. It'd be very stressful. And so pacemakers tend to be a bit stressful on the heart. They work, but they're a bit stressful. It's a far better system to try and recognize the onset of this problem and kind of nudge it. Like if you can look at the butterfly and you recognize, oh, it's going to flap its wings, and just stop it. You just stopped a hurricane. You did a little bit of work and stopped a hurricane from being produced. So if you can just recognize your heart is going to go into fibrillation and nudge it so it beats normally, it means that your heart is much less messed with. Jet engines, spotter. If you can recognize when they're going to flame out, stop it. So it's very useful. None of that's in the textbooks. It's in the graduate textbooks, but none of that's in the textbooks. But eventually there'll be some part of it there. So big rooms, big oceans, lots of convection. Little room, well, not a little room, but a little package of air, little package of water, not so much. And that's interesting, actually, because there's an amazing thing called, I want to go back a little bit. There's an amazing thing called a string vest. So my dad, different generations have different fashion senses. I never wore an undershirt. I just never grew up with one. We always just, my generation, in England, we just wear shirts. Used to drive my mum crazy because the undershirt was there to kind of keep your shirt somewhat clean. I've told you about our hygiene habits in Europe before, I think, about bathing, not bathing that much. Well, not washing shirts that much as well. It was an issue. So undershirts were like important. And then my generation came along and, my mum's going, why are you wearing a vest? We call them vest. Man, they're not fashionable. I don't care. She'd go, But we were teenagers, so eventually she gave up. My dad never gave up. He wore his vests. We were actually quite a poor family when I think about it. And my dad would wear a vest until literally he could not wear it anymore. So it got holes in it, rips. And it became a joke, family joke. He'd be shaving and his vest would have more holes than cotton. And we say, oh, it's Dad's vest, it's ripped to pieces. And then there was a fashion trend, and it was the so-called string vest. It looked like a ridiculous joke. It was a vest that literally had cotton strings in it. It was all holes. And my aunt got it for my dad. And I pulled it out of the bag and we all laughed and we said, oh, the holes are already in it, Dad. You don't have to make your own holes. They're already in it, so it's going to work. And he's looking at it going, what the heck is this? So he put it to one side. And then one day, about a month later, he comes home and he's beaming. It used to be cold and damp in Britain. Really cold and damp. You'd get these days when it would rain and you'd get a headache from the rain because it was so cold. It was like pouring ice water over you, like for most of the day. And we'd wear layers of clothes to keep warm. It was all cotton and wool, so you'd wear layers of clothes, and you'd take your jacket off, you take your overcoat off, you take your jacket off, you take your cardigan off, and you'd work, and you'd put it all back on, and you'd go out again. He comes home and he's beaming. What happened? Oh, this vest is the best thing ever. Going, you're joking. He goes, no, you got to. I'm not wearing one of those. It make you toasty warm, he said. So then he gets me one. I'm like mortified. I've got a string vest. You just try it once, he says. So one day it's really cold. I put it on, and I am so warm. It is delightful. So I go to my physics teacher and I go, why is this working? We've got holes in the thing and it's keeping me warm. I mean, this makes no sense. And what he pointed out to me was like, if that's your skin and you have string and then you have a shirt, you trap in little envelopes of air. And those little envelopes of air can't convect. They're going to conduct. And air is a really poor conductor. If it's not convecting, it's really good insulator. The problem with air is it convects, and it's a real pain when it convects. So you get these weird situations where string vests rely upon the conductivity, the conduction of heat through air, not the convection. So very interesting. Radiation basically is just things glow. Light glows off. If you've ever seen a neon light, it's kind of like neon lights, except that the reason why a neon light only has one color is because the gas is so low pressure inside. Those gas particles, they don't know there's any other gas particles in there. So they're all identical. But when you get atoms and they know about each other, then they have this rule. They're like people. They like to be individuals. So they change their energy levels. So if I have 3 atoms of hydrogen, I can kind of imagine it as having 3 energy levels. And if I have 3 isolated atoms, they'll be identical. But if I put them in contact by increasing the pressure, then what happens is this one says, oh, I'm going to go a bit lower. And I'm going to pull that one up a bit. And I'm going to put that one a little bit lower. And then this one goes, well, I'm going to go even lower than you are, but here I'm going to go lower. And now I'm going to go higher than you. And if you do that with enough atoms, you go from 3 levels to having a whole bunch, a continuous family of levels with different colors throughout. So what might be a red line here and a green line there and a blue line there becomes red, orange, yellow, Richard of York, green, blue, indigo, violet. We get the rainbow colors from the sun because the surface of the sun is so pressure filled that the atoms know about each other. That's what we're seeing there. We're seeing this rainbow from the sun. Well, that turns out to be the tiniest bit of the light that is in the universe. It's because of the temperature of our sun. If we went a little bit cooler, then we would get infrared. And if we went even cooler, we get microwaves. So your microwave oven is really like one of those easy bake ovens. Except your easy bake oven used visible light. Well, actually, it actually used infrared light. Whereas your microwave is using microwave light. And we have radio waves. So when you see a radio tower, imagine that it's glowing with a light which is redder than the reddest red that you can imagine. But it's glowing. And so if you go over the horizon, you tend not to hear it so well. Now, it's such a long wavelength it can go through walls, which means we can hear it inside rooms. But I can put a metal grid around me and I can keep radio waves out to a fair extent. If I go hotter, then I get ultraviolet. That's the stuff that causes skin damage because it's got more energy. And then we get X-rays. That's the stuff that really causes skin damage, which is why when you do, you're only allowed so many X-rays in a year. And if you work in that, you have basically lead apron on. And gamma rays, which basically we try not to get around at all. We maybe use them on pipelines and stuff like that. They might be used in medical physics. It's the atmosphere that keeps the gamma rays. It's the magnetic field. Well, it's a bit of everything. The atmosphere keeps gamma rays away from us. It's not the magnetic field. It's the atmosphere that keeps the magnetic gamma rays away from us. Thank heavens for that, or else we'd be toast. We wouldn't be here. So heat transfer through the movement of photons is called radiation, and this mechanism can work in a vacuum. And we say V, that's the speed, is equal to the frequency times the wavelength. Think of the frequency as how fast you step. And think of the wavelength as being how far you step. And you put the two together, 10 steps per minute, 1 yard per step, that's 10 yards per minute. That's how you get the speed out of it. So, what is the wavelength of WMNF 88.5 megahertz? The M stands for 10 to the 6, a million. So we can say, well, V equals F lambda. Lambda, that's lambda, is equal to V over F, which equals V is 3 times 10 to the 8. You don't need to know that. And F is 88.5 times 10 to the 6. So that's going to be, well, did I bring a calculator? Which one is it? 3.4. 3.4 meters, thank you. 3.4 meters. So public radio, community radio, that's our local radio station, sends light. It's red light, redder than you can imagine, through the neighborhoods, and from one crest to the next crest is about 14 foot. That's how long the wavelength is. And that's if you could look over towards the tower, you would see it brighter over there, because that's where it's coming from. We can't see it, but it's light like that. That long wavelength can get through concrete walls and everything. You don't really notice them because they're not really substantial enough. You don't need to know that. That's just for us to talk about. And then what is the frequency of a 2 centimeter microwave? So V equals F lambda. So what's the frequency? F is equal to V over lambda. So this is 3 times 10 to the 8 over microwave. Centimeter in your. So here's a trick if you want. Get a chocolate bar and put it in your microwave. Kind of break it so you have a big long length of chocolate going across your microwave. Take the turntable out. You don't want this thing to spin. And you might maybe use 3 bits of chocolate, And then turn your microwave on for like 2 seconds and look, and then 3 seconds and look, and 4 seconds and look. And what you'll find is, if I look from the side, it kind of goes like this. It goes. It melts in some bits. There's bits where it melts and bits where it doesn't melt. And the bits where it melts is like the peak of the wave, where the wave is really vibrating. And the bits where it doesn't melt is like the still part of a wave. And then there's a bit where it's really vibrating in the still part. It's because it's like a guitar string. It's a standing wave. And so you can measure from the melted bit to the melted bit, and you get about 2 centimeters. So you can work out the wavelength of your microwave. And then what you can do is you can say 3 times 10 to the 8 over 2 times 10 to the minus 2. 2 times 10 to the minus 2 centimeter, yeah? That's going to equal 1.5 times 10 to the 10. Oh, I'm sorry. That's centimetres per second. I'm in centimetres. I shouldn't really be in centimetres here. So that would be, this is, again, more than I want you to know, but 2 times 10 to the minus 2 centimetres. Oh, no, that's right. So that would be in metres per second. Let me just check about that. F equals V over lambda, so that's V over lambda. Yeah, I'm sorry. So that's hertz. That's how fast your microwave is oscillating. Now, to go back to what we're saying, if you take your chocolate bar and you measure the wavelength, and you know lambda is equal to 2 times 10 to the minus 2 meters, and you know that the frequency of your wave of your machine, it should say somewhere on it, the frequency of your machine is 1.5 times 10 to the 10 hertz. You can work backwards and you can say C is equal to F lambda, which equals 3 times 10 to the 8 meters per second. So using a chocolate bar and a microwave, you can measure the speed of light, which is a pretty good experiment when you think about it. And to make it an experiment when you're finished, which is nice. So all objects whose temperature is above absolute zero glow. So we get, infrared, we get visible, we get. Look at this difference between the ultraviolet galaxy and the light-sensitive galaxy, and look at that. You wouldn't even notice that, but my word, it's there. Yeah, it makes a huge difference. Different temperatures give us different colors. So here's a graph of the intensity of colors versus wavelength for the light, and sure enough we have some colors we can't see, so I didn't put them in. This is the visible red, orange, green, blue, indigo, violet. We say that all substances at temperatures above absolute zero emit radiant energy. The peak frequency, that's the top of this peak, depends upon the temperature, so we get that. We can say that higher temperature, higher frequency. Higher temperature, bluer. Now this is backwards. We think of hot as being red and cold as being blue. But in radiation terms, hot is blue and red is cold. It's like just backwards. I had a friend who was a bit pedantic, and he wanted to change the taps in our company to be the other way around, to be scientifically correct. And the management were going, "You're crazy, you're going to burn people. You're going to scald them with the hot water. It's nonsense." But he was like a purist. Okay. Let's take some surfaces. I'm not going to paint my house black. Why? Well, white light hits the black, but none of it bounces back. It absorbs everything. So my house is going to absorb all the sunlight, which will make my house really hot. I'm going to paint my house white. Forget the silver. I'm going to paint my house white because it reflects all the colours. White light goes in, white light comes out. That means it doesn't absorb this energy. So we talk about things being emitters and absorbers and reflectors. A black object is a good emitter. If it lets the light in, it lets the light out. It's a good absorber. It certainly lets the light in. It's a lousy reflector. But a white surface is a poor emitter. It's a poor absorber. So it's a good reflector. So if you're in a warm environment, you paint your house a light colour. White is best because it reflects the heat. If you're in a cold environment, you paint your house white because it will not emit the heat. Cool. Yes?
So what about the red object and the red light?
So the red object in the red light appears black? No. Appears... So tell me the story.
No, I mean like
So,
will the red light goes out, or?
so if you point a red light onto a red object, it will absorb that light. Will it emit that light? I don't know. I should know, because there's a section on colour, but I don't know. I think it will reflect red light. If you have a green object and you shine red light on it, I think that will appear black. But I'm uncomfortable with my answers. So I'm going to go home and read the book. Almost 1 minute. I think I've almost finished. Greenhouse effect. Energy from the sun comes in infrared, visible and ultraviolet because it's hot. The Earth is not so hot, so it only emits in the infrared. We have a nice equilibrium temperature because we have energy inside us from the formation. We have hot center, but we also get a lot of energy from the sun. We're not as hot as we would be if we didn't emit any heat, but we do. So we lose some heat, we gain some heat. If we had no carbon dioxide in our atmosphere, we would be colder than we are, because carbon dioxide limits the amount of ultraviolet. So if we had no carbon dioxide, all the ultraviolet would get in, but all the ultraviolet would get away, and we'd be colder. We have enough carbon dioxide in our atmosphere that we have our current temperature. But the worrying thing is, if we increase the amount of carbon dioxide in our atmosphere, it will affect the sun's energy getting in a little bit. But most of the energy comes from these two. So we'll reduce this third element by a little bit. But we will affect everything that leaves. It's like you got 3 water hoses on you, and you can turn that one down a little bit, but the other 2 are still going to get you. But in turning that one down a little bit, I'm turning the one that gets the water away from me down as well. So it really affects us disproportionately, because we only glow in the ultraviolet, in the infrared. We only glow in the infrared. We reflect sunlight, we don't glow in it. So more carbon dioxide means more warming. Now, we can argue about whether humans are dominant in that. I believe they are, and I think most scientists believe they are. But we can't argue with the fact that more carbon dioxide means more warming. Can I do these two, and then, because then I'm done. So, which one is not one of the 3 modes of heat transfer? Convection, radiation, and dispersion? No. Which mode of heat transfer does involve atoms moving past each other? Convection. Convection currents. What happens to the rate of energy flow through a rod if the temperature difference between the ends is doubled and its cross-sectional area? So K delta T A over L. If its temperature difference is double, so that's 2 times, and its cross-sectional area is halved, that goes a half. They cancel each other out. It is unchanged. Agreed? I doubled one and a half the other. And then characterize a black tile in terms of its emission, absorption, and reflection. Black tile is a good emitter. It's a good absorber. But it is a lousy reflector. So, cool. Thanks ever so much. I'll see you guys next time.